30 years after its inception, the James Webb Space Telescope was launched from French Guiana on Christmas Day. On December 28th, it passed by the Moon, and on January 24th, it fired its engines for 5 minutes before entering its final orbit, which was 1.5 million kilometers away from Earth. After months of tedious setup, it finally generated its first image on July 12th of last year, showing us distant galaxies for the first time as they appeared more than 13 billion years ago. Since then, the Webb telescope has continued to build upon this incredible foundation. It appears that the threshold has been lifted once more, and Webb is ushering in a new era of astronomy and space exploration. Its most recent photographs serve as compelling proof of both humanity's capacity for discovery and its complete insignificance. Join us as we explore the new image captured by the James Webb Telescope that reveals the secrets of the universe. In actuality, telescopes are not physically peering back in time when they observe the light from distant galaxies. No one is able to directly gaze at the past because it no longer exists. Instead, the telescopes are observing the current pattern of a beam of light. This beam of light has been essentially undisturbed for millions of years as it moves through the mostly empty vacuum of space. As a result, the pattern of this light beam at the present time is the same as the pattern it had when it was first produced by the far-off galaxy millions of years ago. We can therefore infer about the galaxy's appearance millions of years ago by observing a beam of light in its current state. It's comparable to printing out a baby photo of your daughter and then looking at it 10 years later. You are metaphorically looking back in time when you look at the printed photo to see what your daughter looked like as a baby. However, you are not actually seeing back in time. Your daughter is not a baby anymore, and she doesn't have a baby self anywhere in the universe. Instead, you are viewing a current lighting pattern that was produced by the printed photograph as it's reflecting the light in the surrounding space. However, the current beam of light emanating from the picture has the same pattern as the beam of light that originated from your baby daughter 10 years ago because the ink in the picture has been specifically organized into a pattern resembling your daughter as a baby, and because the ink pattern has not changed over the past 10 years. Similar to this, we can only infer the past from present-day light beams hitting observatories directed at far-off galaxies if the light has not altered through time. A more accurate portrayal of the past would result. The redshift that results from the universe's expansion is one significant alteration to light as it passes across intergalactic space. Fortunately, since the redshift is now well understood, it is possible to shift the light pattern back by the proper amount to provide an accurate picture of the distant galaxy at the time the light was emitted. Just a few galaxies that were previously known to exist in the period the James Webb Telescope has now revealed hundreds of ancient galaxies that might be among the first inhabitants of the universe. According to a recent study, these very young galaxies displayed intricate structures and star formation clusters as early as 600 million years after the Big Bang. The study is a result of international cooperation known as the JWST Advanced Deep Extragalactic Survey, which collected data over the course of a month from two inconspicuous regions of the sky, one in the vicinity of the Fornax cluster and another in the constellation Ursa Minor. Over 700 recently discovered young galaxies in this area provide insight into the early universe. If you took the whole universe and shrunk it down to a 2-hour movie, you were seeing the first 5 minutes of the movie. Kevin Hain, an assistant research professor at the Steward Observatory in Arizona and a lead author of the new study, said while announcing the discovery. These are the galaxies that are beginning the process of creating the constituent parts and complexity of the modern world. Recent discoveries using Webb's data have clarified the origins of early galaxies and stars, which gave rise to the diverse range of elements seen in the universe today. Payne and his team discovered 717 young galaxies in just those 5 minutes, indicating that the universe is between 370 million and 650 million years old. These galaxies are already thousands of light-years across, have intricate structures, and are giving birth to stars in numerous clusters. Previously, the earliest galaxies we could see just looked like little smudges, yet those smudges represent millions or even billions of stars at the beginning of the universe. Now we can see that some of them are actually extended objects with visible structures. Nearly all of the main space telescopes, including Hubble, Chandra X-ray Observatory, and NASA's now-retired Spitzer, have conducted substantial research on the two locations used in this study, collectively referred to as Good South. 93% of the newly discovered galaxies that Webb discovered during JWST had never been observed previously despite this prior examination. Only the brightest, most extreme instances of brilliant galaxies from the early cosmos were visible to us before. Now that the cosmos is still young and tumultuous, we are actually drilling down to more common, everyday galaxies. There's been much discussion on how exactly that chaotic, extremely dusty environment became the transparent universe we know today. One popular theory holds that this stage of the universe's evolution, known as the epoch of reionization, happened about 400,000 years after the Big Bang, when the first generation of stars, estimated to be 30 to 300 times as massive and millions of times brighter than our Sun, formed and illuminated the previously dark universe by dividing the cosmos's plentiful hydrogen atoms into protons and electrons. This ultraviolet starlight reionized the universe, a process that continued for 1 billion years after the Big Bang. Few researchers, however, believe that outflows from supermassive black holes, like the one in the center of our Milky Way, may have caused ultraviolet radiation from galaxies to escape and as a result may have had a more significant impact on cosmic development than previously assumed. Now, a second JWST team that has been researching galaxies between 5 and 850 million years after the Big Bang, or between 5 and 8 minutes of the 2-hour movie describing the universe, believes it has the solution to the age-old query. In this next scene of the universe, we are starting to actually see the impact of galaxy formation on the composition of the large-scale universe. Galaxies in the very early universe were just far more chaotic in general in how they formed stars. In order to understand how starlight ionized the gas within those extremely early galaxies, Einstein's team examined the signals of star formation in those galaxies, a property that atoms ionize by starlight radiating when they have cooled and merged with other molecules. The researchers discovered that 1 in 6 galaxies at the time displayed severe line emissions in the galaxy spectrum. These emission lines show that early galaxies were producing stars actively, which led to torrents of ultraviolet photons being blasted into each galaxy. As a result, the early stars of the cosmos turned into the primary forces for cosmic reionization. Sly claims that in the very early universe, these strong emission lines are actually very typical. These remarkably strong emission line fingerprints, which indicate intense recent star formation, are present in almost every galaxy that we have discovered so far. They were excellent at producing hot, massive stars in these early galaxies. Einstein's team deduced from the same emission lines that galaxies in the early cosmos gave birth to stars in brief bursts and then went dormant periods. A deep-fielded image of hundreds of galaxies, many of which were seen as they were in the early cosmos, was the first image the James Webb Space Telescope sent back on July 22. Many folks weren't prepared for some of these galaxies to appear to be curiously deformed and twisted. It is an illusion in the Webb photos. These Salvador Dali-like galaxies that resemble melted candy are not how these objects appear in space. A further surprising feature of the Webb photos is the appearance of many galaxies in the same image, as shown in the image of the huge galaxy cluster RxJ 2029. Once more, this is a delusion. These galaxies do not actually have identical twins. How is that even possible? The same gravitational lensing mechanism is what causes these two separate Webb image features. Albert Einstein's original prediction of gravitational lensing, which functions as a magnifying glass for astronomers, was made more than 100 years ago. They are all examples of gravitationally lensed objects, which are warped and repeating galaxies. Einstein's theory of general relativity contends that mass-having objects have an impact on the fabric of space and time, which are combined to form a single entity known as spacetime. Gravitational lensing can be imagined as a stretched rubber sheet covered in balls of varying densities. The rubber sheet is more severely warped by a ball with a larger mass, similar to how massive objects embedded in spacetime warp it. Galaxies and galaxy clusters are particularly extreme examples. When light from a background object like a star or galaxy traverses this warp, the effect becomes fascinating. Normally, light moves in straight lines, but when it passes through distorted space, it bends due to the way mass warps space. As a result, the background object appears to be in a different part of the sky when the light reaches Earth. Extreme warping occurs when a large object is between Earth and the background source, causing light to travel along various routes that are all warped to varying degrees. This modifies the light's arrival time and length of the journey before reaching us. As a result, a lensed object may appear at many locations during a single exposure, resulting in intriguing patterns such as crosses or Einstein rings, which are composed repeated instances of the same thing. According to the European Space Agency, galaxy clusters are not ideal lensing objects due to their messy form and lack of a concentrated distribution of mass. This results in background lensed objects appearing warped as arcs around the lensing galaxy cluster. However, these lensing artifacts are more than just fascinating objects to look at. Astronomers can benefit from gravitational lensing in various ways. In addition to distorting background light, gravitational lensing can magnify background light, enhancing feeble light from extremely far-off objects like early galaxies. Gravitational lensing is therefore essential to Webb's study of the early universe. Additionally, lensing objects can reveal a lot about themselves through the patterns they produce when light flows through them. For instance, gravitational lensing can show the distribution of mass in galaxies and galactic clusters. Furthermore, the James Webb Space Telescope has observed the exoplanet WASP 18b, a gas giant 10 times more massive than Jupiter orbiting its star at an extreme distance. Despite its extreme heat, the telescope's observing abilities allowed researchers to detect water vapor in its atmosphere, showcasing Webb's amazing sensitivity. WASP 18b is tidally locked, meaning one side always faces the star, leading to large temperature disparities on its surface. Webb's measurements have provided detailed insights into these temperature variations, revealing potential mechanisms at work such as atmospheric drag or a powerful magnetic field, which would be a fascinating discovery. Overall, Webb's sensitivity has enabled detailed mapping and observation of hot giant planets like WASP 18b, providing exciting discoveries and confirming theoretical predictions. On the other hand, we are rewriting the history of the formation and evolution of galaxies in the first moments following the Big Bang. Webb and gravitational lensing's magnifying ability together represent a revolution in our understanding of the universe. 40 light-years from Earth, where every day can be likened to a windy beach purgatory, the adage "a bad day at the beach is better than a good day at the office" would not apply on exoplanet HD 28185b. Sand particles that are hot and abrasive whirl in the clouds. Visitors might get a terrific exfoliating facial from the weather, but it wouldn't be at all soothing. Temperatures soar to a blistering 1,500 degrees Fahrenheit. Up in the clouds, it's a relentless, scorching sandstorm. Additionally, rainstorms likely pelt the planet with a sandy mixture when the clouds become too dense. According to scientists, smaller silicate granules that make up its atmosphere resemble smoke more than anything else, while the bigger particles may resemble hot, minuscule sand grains. Meanwhile, James Webb Telescope observations reveal a place with considerably more extreme conditions and some parallels to Earth. For instance, they found that the atmosphere of the planet clearly showed the presence of chemicals that are abundant on our planet, such as water, methane, carbon monoxide, and carbon dioxide. Our days and their days are only separated by 2 hours. However, it takes 10,000 years for one of its 2 stars to complete one full orbit. It was compared to Tatooine by a NASA Twitter account, alluding to Luke Skywalker's home in Star Wars, which featured twin sunsets. Their light wouldn't shine so brightly, given how far away the planet is from its home stars, about 4 times farther than Pluto is from the Sun. Some light wavelengths or hues are absorbed by molecules in the environment. Astronomers can determine what light segments are missing to determine the molecular composition of the atmosphere by dividing the light into its parts, creating a rainbow. Exoplanet spectra, which are used to examine the atmospheres of other planets outside our solar system, are one of Webb's main goals. Webb's observations have already begun to shed light on the atmospheres of various exoplanets, providing invaluable data for understanding their compositions and environments. The James Webb Space Telescope represents a significant leap forward in our ability to study celestial bodies beyond our solar system. Its advanced capabilities allow astronomers to peer deeper into space and further back in time than ever before, unraveling mysteries of the universe's origins and evolution. Webb's observations of distant galaxies and exoplanets provide crucial data for theories about how stars and planets form, and how they evolve over billions of years. By studying the light emitted by these celestial objects, Webb helps scientists understand the chemical makeup of atmospheres and the conditions under which planets may harbor life. Moreover, Webb's ability to detect faint signals from distant objects enables researchers to study phenomena such as gravitational lensing, which provides insights into the distribution of mass in the universe. This phenomenon, predicted by Einstein's theory of general relativity, allows astronomers to magnify and study distant galaxies that would otherwise be too faint to observe directly. In addition to its scientific achievements, the James Webb Space Telescope represents a triumph of international collaboration and technological innovation. Built by NASA in partnership with the European Space Agency, ESA, and the Canadian Space Agency, CSA, Webb embodies the shared ambition of scientists and engineers from around the world to push the boundaries of human knowledge and exploration. The development and construction of Webb involved years of meticulous planning, engineering challenges, and rigorous testing to ensure its readiness for the harsh environment of space. Its deployment and operation require precise coordination and expertise from teams on Earth to operate the telescope and analyze the vast amounts of data it collects. As Webb continues to operate and deliver groundbreaking discoveries, it inspires the next generation of scientists and engineers to pursue careers in space exploration and astronomy. The telescope's ability to capture stunning images and unravel mysteries of the cosmos captivates public imagination and fosters a deeper appreciation for the wonders of the universe. Looking ahead, Webb's scientific mission promises to unlock further secrets of the universe, from the formation of galaxies and stars to the search for potentially habitable exoplanets. Its observations will continue to shape our understanding of the cosmos and our place within it, offering new perspectives on the fundamental questions of existence and our origins. In conclusion, the James Webb Space Telescope stands as a testament to human ingenuity and curiosity, pushing the boundaries of what is possible in space exploration. With its advanced technology and unprecedented capabilities, Webb is poised to revolutionize our understanding of the universe and pave the way for future discoveries that will shape the course of scientific inquiry for generations to come.